Welcome to today's deep dive. I'm your host, and we have a pretty mind-bending topic to get into today.
We really do. I'm your resident expert for this dive.
Yeah.
And I have to say, um, this one completely shifts how we think about machine learning.
Yeah, so to start us off, I want you to just think for a second about how you as a human actually learn. Like, if you want to learn to use a brand new word in a sentence, you don't need 10,000 examples.
Right, definitely not.
You usually just need a definition
Uh-huh.
and maybe one example, and your brain just kind of snaps it into place.
Yeah, you hear it once, and you can instantly use it in totally different contexts.
Yeah.
We are essentially few-shot learners. We only need a few examples to pick up a new task.
Exactly. But historically, artificial intelligence has absolutely not worked that way, which brings us to our focus today. We are looking at a landmark research paper from OpenAI titled Language Models Are Few-Shot Learners.
And this is the exact paper that introduced the model GPT-3 to the world.
Right, and we're exploring how this specific model attempts to move AI away from specialized training and toward that generalist adaptation you just mentioned, and we'll see if it actually works.
And to understand if it works, you have to understand the sheer scale of what they built. We were talking about a model with 175 billion parameters.
Which is just a staggering number to even visualize.
It really is. To put it in perspective, at the time this paper came out, that was 10 times larger than any previous non-sparse language model. It was a massive leap.
So let's step back a bit and talk about the old way first, because I think that really highlights why this paper is such a paradigm shift.
Yeah, the old way in natural language processing was something called fine-tuning.
And that involves taking a model that's already trained on a bunch of text and then basically sending it back to school for one specific job, right?
Exactly. Let's say you want your AI to translate English to French. Under the fine-tuning paradigm, you would have to gather a specialized data set of thousands and thousands of English-French translation examples.
Just a massive amount of highly specific data.
Right, and then you feed all that into the model to perform what are called gradient updates. You're fundamentally retraining the model. You're changing its internal weights just so it can do this one specific task.
Which makes it a very narrow expert. Like, it might be incredible at French translation now, but it completely lost its ability to summarize a news article or, write a poem.
Precisely. You need a massive new data set for every single new task.
But the alternative presented in this paper is totally different. It's called in-context learning.
Yes. The researchers basically asked, what if we just make the pre-trained model so unimaginably large that it learns how to learn?
Right, so instead of rewiring the brain with gradient updates, you just talk to it. You give it a prompt.
And the paper breaks this down into three specific definitions: zero-shot, one-shot, and few-shot learning.
Let's walk through those for everyone listening. Zero shot is basically the ultimate test, right?
It is. Zero-shot is when you give the model an instruction with absolutely no examples. You just type, translate English to French, give it the word cheese, and an arrow.
And you just cross your fingers and hope it outputs fromage.
Exactly. You're hoping that somewhere in its massive 175 billion parameters, it learned the concept of translation during its initial internet-wide training.
Which is incredibly hard for a machine. But then you have one-shot learning.
Right. One shot is where you give it exactly one example before asking the question. So you say, sea otter equals loutre de mer. Then you ask for cheese.
Okay, and then the main event, few-shot learning.
This is where GPT-3 really shines. In few-shot, you give the model between 10 and 100 examples right there in the prompt, what we call the context window.
So you're establishing a clear pattern.
Yes. You show it 10 different English words and their French translations, and then you ask for the 11th. And the key takeaway here, the absolutely critical point, is that there are no gradient updates happening.
The model isn't actually retraining itself.
No, it's just reading the prompt, picking up on the pattern you're laying down, and predicting what comes next based on everything it learned during its massive pre-training.
It's adapting on the fly. And the paper shows that just by scaling the model up to that 175 billion parameter mark, this lazy few-shot method starts to perform incredibly well.
It really does. Which brings us to the benchmarks, because they threw everything at this model to see where it would break.
Let's talk about the SATs,
Oh.
because I think anyone who took the SATs remembers the dreaded analogy section.
No, absolutely. Audacious is to boldness, and then you have to pick the matching pair of words. It's a tough test of semantic reasoning.
Right. And GPT-3, operating only in that few-shot setting where it's just given a few examples in the prompt, achieved 65.2% accuracy on that task.
Which might sound like a D- in high school, but you have to look at the baseline. The average score among human college applicants on that exact same test was 57%.
Wait, so the AI literally beat the average human college applicant on complex analogies.
Handily. And it wasn't fine-tuned for the SATs. It just figured out the logic from the context window.
That is wild. But, okay, let's look at straight-up knowledge. The Trivia QA benchmark.
Right. This is a test of factual trivia. And they tested GPT-3 in what's called a closed book setting.
Meaning it couldn't browse the internet to find the answers, it had to just rely on its own internal memory.
Correct. And it scored 71.2% accuracy.
Wow.
Yeah, and what's crazy is that it outperforms state-of-the-art systems that were specifically fine-tuned for trivia tasks. It just absorbed that much knowledge from its training data.
It essentially memorized the internet. But this is where the paper gets really fascinating, because the illusion of intelligence starts to get a little complicated when they asked it to do math.
Yes, the arithmetic tests. This is incredibly revealing about how language models actually work.
Because it's a supercomputer, right? You'd think asking a computer to do math is the easiest thing in the world. But they didn't give it a calculator tool. They just asked a language model to predict the text of a math problem.
Right. They gave it 2-digit addition, 3-digit addition, all the way up to 5-digit math. And on 2-digit addition, it was flawless. 100% accuracy.
Okay, makes sense. What about 3-digit?
Still pretty good. Around 80% accuracy.
But then it tries 5-digit addition, like adding 14,000 to 22,000.
And it completely falls apart. The accuracy drops to around 9 or 10%.
Which is completely counterintuitive. Why can a supercomputer add 50 and 50 but fail at larger numbers? A cheap calculator from the 1980s can do 5-digit math instantly.
Because GPT-3 isn't actually calculating anything in a traditional sense. It's predicting the most likely next tokens of text.
Ah, so it's just guessing the shape of the answer.
Exactly. It has seen things like 2 plus 2 equals 4 millions of times in its training data. It has memorized the visual rhythm of small math problems, but it doesn't have an underlying calculator engine.
It's just mimicking the process. The paper even notes that it frequently fails to carry the 1.
Right, it makes textual errors, not mathematical ones. It's doing an incredible impression of someone doing math without understanding the core logic.
It's simulating competence, which is a really crucial distinction to keep in mind, especially when we move to the next section of the paper. Because when it comes to writing text, that simulation is so flawless that it actually gets kind of scary.
You're talking about the news generation experiment, the Turing test moment.
Yeah. The researchers wanted to see if actual human beings could distinguish between a real news article and a fake one generated completely by GPT-3.
So their methodology was straightforward. They gave the model a real title and subtitle. For example, United Methodists agree to historic split, and asked it to write a 200-word article based on that prompt.
Then they took those AI articles, mixed them up with real news articles, and showed them to 80 human participants in the U.S.
And asked them to spot the fake.
The results here are the defining statistic of this whole paper for me. Human accuracy in detecting the AI-generated fake articles was roughly 52%.
Which, if you think about it, is essentially random guessing.
Yeah, 50% is a coin flip. Humans could barely tell the difference.
And for some specific articles, it was much worse. For that United Methodist article you mentioned, the human participants were only 12% accurate in identifying it as AI.
Meaning 88% of the people who read it thought it was written by a human journalist.
Yes. The text is coherent, it flows logically, the grammar is perfect, it completely bypasses our usual spam detectors.
And the paper dedicates a whole section to the implications of this, right? The misuse section. Because the barrier to creating high-quality misinformation just evaporated.
It's a massive shift in the economics of disinformation. Previously, writing convincing fake news or targeted phishing emails required human labor. It was expensive and time-consuming.
But with a model like this, you can generate infinite convincing variations of a narrative almost instantly.
Exactly. It lowers the barrier to entry for anyone wanting to run an influence operation or a phishing scam because the text is just that good.
So we have this wild dichotomy. We have an AI that can fool us 88% of the time on news, but it completely fails at 5-digit addition. It's like a brilliant savant with glaring blind spots.
That's a great way to put it. And the paper points out another massive blind spot, which is common sense physics.
Right, the classic cheese in the fridge scenario.
Yeah, if you prompt the model with a question like, if I put cheese into the fridge, will it melt? It seriously struggles to give the right answer.
Which seems absurd. A 5-year-old knows the answer to that. Why doesn't a 175 billion parameter brain know it?
Because it lacks grounding in the physical world.
Yeah.
It has never seen a fridge or felt cold or held a piece of cheese. It only knows text.
So it's just relying on statistical associations between words?
Right. In its training data, the word cheese and the word melt probably appear close to each other all the time, like in recipes. So the model strongly associates them linguistically, but it doesn't physically understand that a fridge is cold, and cold prevents melting.
It's all syntax and no physical reality.
Exactly. And you see similar limitations in comparison tasks. There are benchmarks like WIC, word in context, where you ask the model if a word is being used the same way in two different sentences.
Like asking if the word bark means the same thing in dog bark versus tree bark.
And GPT-3 is surprisingly bad at those specific comparisons. It also struggles with repetition. When generating really long passages of text, it can get stuck in loops or just drift off into complete non sequiturs.
Because it's just predicting the next word. It doesn't actually have a grand plan for what it's trying to say.
Right. The illusion breaks when you test its physical common sense or its long-term coherence. But there is one area where the model works exactly as its design intended, and the results are incredibly problematic.
You're talking about bias and fairness, the mirror effect.
Yes. Because GPT-3 was trained on a massive scrape of the internet, including Wikipedia, books, and just general web text, it inevitably absorbed the biases present in that data.
It read the internet, so it sounds like the internet, and the researchers didn't hide this. They ran specific tests to measure it. Let's look at what they found regarding gender.
They prompted the model with neutral phrases like, "The detective was A," and let the model fill in the rest. They tested this across 388 different occupations.
And what was the split?
For 83% of those occupations, the model leaned heavily toward male identifiers.
So the detective, the banker, the boss, all defaulted to he.
Consistently. Meanwhile, occupations like midwife and nurse leaned heavily female.
And they saw similar reflections of societal bias when it came to race and religion, right?
They did. They ran sentiment analysis on generated text and found that the word Asian consistently had high positive sentiment scores, while the word black consistently generated text with low sentiment scores.
It absorbed the stereotypes embedded in the text it read.
And with religion, the word Islam co-occurred with words like terrorism and violent at a dramatically higher rate than other religions.
Now, a really important point here for the listeners. The researchers did not intervene to fix this in the model before publishing, did they?
No, they didn't. And they were very explicit about why. They analyzed it to show the scientific community that these immense models act as a mirror. They retain and even amplify the stereotypes of their training data.
They impartially presented it as a warning label. If you train a model on human society, you get all the flaws of human society right back.
Exactly. They are demonstrating the reality of the data set.
All right, so let's zoom out and pull this all together. We are looking at a 175 billion parameter model trained on roughly 300 billion tokens of data.
It proves that if you make a model big enough, you can largely abandon specialized fine-tuning. It becomes a few-shot learner just by being asked.
But the results are a mixed bag.
Yeah.
It beats humans at complex analogies. It blurs the line between human and machine text so well that we can barely detect it, but it still doesn't understand basic physics or social fairness.
That's the state-of-the-art presented in the paper.
So, keeping all of that in mind, I want to leave you, the listener, with a final provocative thought to mull over. The paper clearly suggests a scaling law, meaning the model's performance improved linearly as it got bigger. We haven't hit the ceiling yet.
Far from it.
So if a model with 175 billion parameters gets us to a point where human beings literally cannot distinguish fake news from real news, what exactly happens when the next generation of models is 10 times larger? Are we ready for an era where our entirely in-context reality is completely indistinguishable from actual reality?
That is the big unknown we are all heading toward.
A huge thank you to our expert for breaking down this massive paper today, and thank you to everyone for listening to this deep dive. We will catch you on the next one.